going to be talking about independent events today. So we just covered conditional probability, and independent events have a lot to do with conditional probability. So we're going to look at how they relate to each other. Then we're going to actually define what an independent event is mathematically. Then we're going to modify that multiplicative rule or multiplication rule from conditional probability for independent events. All right, so first things first, independent events and how that fits together with conditional probability. Well, before we talked, you could think about, let's say, non-independent events. Non-independent events means this. If knowledge of one of the events, of the outcome of one of these events, affects the probability that the other event occurs. So if I know that they are male, does it affect my estimate of whether they own a laptop or not, right? If I know that this person is obese, does it affect my estimate for whether they might have heart disease, right? Those are what we call non-independent events. Knowing one thing, it changes your estimate of the second event. So here, what you could think about is this. The conditional probabilities for, let's say, knowing that given that this person is, let's say, obese, right? That will change your estimate of heart disease. Versus if you knew this person was not obese, right? These two estimates of heart disease would be different. So they would be not equal to each other, right? So here, that's what we mean by the conditional probabilities are different. If you knew one of the conditions, that would change your estimate for the other event. Okay, now, what are independent events? Well, this means that knowledge of one event does not change or affect the probability that the other event occurs, right? So here, the conditional probabilities are the same. So the probability of heart disease given the color car you drive equals red, right? So if you drive a red car versus the probability of heart disease, oops, shouldn't be slanted, given not red car, right? These probabilities should be the same because presumably car color has nothing to do with heart disease, right? And so you might say, hey, they're independent. Your choice in car color just doesn't have any bearing on my estimate of the probability of your having heart disease. Okay, so now let's talk about this a little bit more mathematically. So let's use this example of obesity and gender, right? So here's obesity on this side and gender on this side. And does the probability of being male or female change whether you might be obese? Does knowing whether somebody is male or female, does knowing their gender, does that affect the probability that they might be obese? Well, it turns out that the probability of being obese given male is 20 out of 100, right? So that's that conditional probability where we're only looking at this world, right? But the probability of obese given that they're female is also 20 out of 100, right? So here you could see that these probabilities equal each other. The probability of being obese when male or not given male or not male are the same. All right, but how about education? Well, is the probability of being obese given that they have a post-high school education, is that going to be different than the probability of being obese given that they only have a high school education? Well, so the probability of obesity given post-high school will be 20 over 100, right? So this is my universe, and it's 20 over 100. But the probability of being obese, given high school only, right, is 30 out of 100. So it's slightly higher for people who haven't had post-high school education than people who have had high school education, who have had post-high school education. Now, these conditional probabilities don't mean that this causes this. It's just that knowing one fact about this person helps you estimate their obesity probability differently. So here, you could see these are not equal to each other. Okay, so now let's define what an independent event is. So we've already talked about this. One way to define it is that the probability of A given B is equal to the probability of A given not B, right? So those two equal each other. It doesn't matter whether B occurs or not, right? And so that's what I have written down right here. But there's another way you could think about this. The probability of A given B is equal to just the probability of A in any circumstance, right? So this is another way of defining independent events. So let's look at that with this data set. So what is the probability of obesity given male? And is that the same as the probability of general obesity? Well, let's calculate that. So the probability of obesity given male is 20 out of 100. But the probability of obesity overall is over here. So it's obesity over all the people in the sample. So it's 40 out of 200. And those are exactly the same proportion, 20%. So, so here we see, yes, being male and being obese, they're independent events in this example. Okay, so now that we know how to define independent events mathematically, now let's talk about the multiplication rule for conditional probability. Previously, remember those trees? What we found was that if you wanted the probability of A and B, that is equal to the proportion of A given B multiplied by the probability of B. So think about this space is now B, and what proportion of that is A given B? If you multiply those together, you get that raw score for that amount. So this is what we call the multiplication rule for conditional probability. And out of this, you could also get the definition of conditional probability, where probability of A given B equals the probability of A and B over the probability of B. So really, they're all the multiplication rule. I'm just like moving stuff around. And I should also say here that obviously you could also have probability of B given A times the probability of A, because you always want it out of that entire, the world that you're living in, the condition that you're living in. But with independent events, we now have a slight change in this. Because the probability of A given B equals the probability of A, look at this rule again. All we have to do now is this. In order to find the probability of A and B, since this equals this, right, A given B equals probability of A, we can now just do probability of A times the probability of B, right? Because this is exactly equal to the probability of A given B, right? So for independent events, we can like simplify this, but it really all goes back to the multiplication rule. But note that with independent events, now you could just know probability of A and still be able to calculate probability of A and B. The other way that you could think about this is obviously you could change it into figuring out different relationships among these things. But you can also generalize it to more than just 2 events. We could put 3 events. Probability of A, B, and C equals the probability of A times the probability of B times the probability of C. And you could do it with 4 events and 5 events. And independent events are nice because you could do this ad infinitum. The way I like to think about this is sort of going back to those sample spaces, thinking about these independent events as little slots that you could fill, right? So let's think about flipping a coin. Those are independent events. Knowing that your first flip was a head doesn't do anything for my next flip of the coin, right? It's still 50-50 chance of getting heads, right? And so here you could think about it as the probability of A. Probability of getting heads is 50%, 50%, 50%, right? So you could see that, you could go on and on and on. And flipping coins are a really classic example of independent events.